Glad to meet you here. I'm Zheng from Shopee. Today I would like to share you something about invalid memory access. Shopee is the leading e-commerce platform in Southeast Asia and Taiwan. Our Shopee app is used by tens of millions of consumers daily. When developing such kind of super app with a huge amount of consumers, we've encountered different kinds of challenges. One of these challenges is that we've received many memory corruption issues online. And for this kind of issues, they are really hard to reproduce and hard to trace the source and detrimental to the customer experience. There are some patterns for crashes caused by invalid memory access. One of them is that the Objective-C message send function or reference counting or deallocation function appear at the top of the backtrace. And usually they are caused by memory errors. And another pattern is the unrecognized selector in the stack trace in the crash report. Perhaps you're sending a message to a ready freeze object, and perhaps someone else mangled the object's content from another thread, and perhaps you're writing to a read-only memory. All of this could cause the invalid memory access. For this kind of memory issues, how to debug? Actually, there are some tricks. First of all, we can get more information from crash reports. A crash report contains much more than the stack trace. We can find clues from the exception type, the register state, and the address offset for the assembly code. We can use Hooper to disassemble. Well, here you may say, wow, assembly code. That is too far away from our daily life and object-oriented language. But I would like to say, just don't be afraid, just explore. It may be easier than you thought, but it is a little different from the language we used in our daily life. And besides, there are some useful user guides online for beginners. Maybe you can just spend half a day and learning how registers work and how stack grows when the function call and how some basic instructions work in the ARM64. So let's start with an example. First of all, we can take a look at the exception type, which is the crash reason. In this case, the operating system sends a segment violation signal when the app is trying to access an invalid address. And this is an exe bad access exception. So let's go back to the backtrace in the crash report. Let's take a look at the function at the top of the backtrace in the crash report. So this is a Objective-C message send function with a hexadecimal decimal value 16 as its offset from the basic address of the message send function. So the offset in the crash report here, it is in decimal value, so we should firstly convert it into hexadecimal value, which is 10. And then we can open Hooper to disassemble this Objective-C runtime dynamic library. We can search this Objective-C message send function, and we can know the base address of this function is 6080 plus we can plus this value with a 10 offset and figure out the exact exact line of assembly code in this binary where the crash happened. So this figure is AF90. This is the line of code the error happened. Here, let's go to the detail. In the beginning of the message send function, here comes a compare instruction. It's simply used to compare two operands. Here it compares the value inside the register 0 and the value 0. So as we know before, the register 0 stores the value of the self pointer. So here it is used to compare the self pointer and the value 0. The next is a branch if that's instruction. This branch less equal instruction can work together with a compare instruction. They can be seen equivalent to the if condition statement. So these two lines of assembly code actually is equivalent to the if self less or equal than 0 return. This is to make sure self pointer is a new or tagged pointer. Then the third one is load instruction. Load instruction is to load data from an address to a register. This is the destination of the register. So here it is to load data from the register 0 to the register 13. So it comes a AND instruction here. An AND instruction is used to perform the bitwise AND operation in the assembly world. As we know before, the register 0 stores self pointer value, and the value in the register 13 is from register 0, so the register 13 actually stores the self pointer value now. Here, firstly, it apply the bitwise operation to the self pointer and this FF8. FF8 actually is a mask in Objective-C runtime. After this AND operation, it comes out its value as a result. Then it tries to put its value to the register 16. So finally, we come here, the line of assembly code where the exception happened when you try to get the access of the imp. Firstly, it adds is a value in the register 16 with the offset value 10, and it comes up with the imp address. Then it try to put this address into the register 11. We can check this in the register state. The value in the register 16 is AF80 plus 10 is 90, and the 90 and the address ends with 90 actually is equal to the address appearing in the exception section in the crash report. So it says the crash happened when trying to load address of this try to load access this memory address, but this is an invalid access. This is an invalid memory access. So you may wonder what's going wrong with this field and why it is an invalid address now. As we know, in normal cases, a field refers to the class for current objects, which can be used in imp lookups. And after this object got released, release function rotates the is a value, so the is a value isn't valid anymore after the object got released. So it turns out this is a use after freeze case, where you attempt to send a message to a already freezed object. However, we still don't know who is the already freezed object. We have to go back to find more in the crash report. And we can see the second function in the backtrace comes from the field, the BT manager file, and in the line number is 104. However, in these lines of code, we can see there are two places triggering the message send function. For the first one is the getter method for the property request ID map. The second one is the remove all objects. Luckily, we still can get help from the offset value. As what we did before, we have to convert it to the hexadecimal value. So we convert the 292 into the hexadecimal value 124. We can get the base address of the function from Hooper, and we get the offset value from the crash report after we convert it into the hexadecimal representation. After adding these two values, we got the address of this address 8494, and then we use Hooper to jump to the offset. There is a trick here. Actually, the 8494 is the address of the next instruction after the object send message is called successfully. But in our case, the message call function, the message send function is failed. So we should focus on the previous address, the previous instruction 8490, which is a branch instruction called message send function. This is what we expected. Now we know the exact line of assembly code triggering the message send function. What we have to do next is to find out the arguments passed into this message send function. We can focus on the X1 register because it stores selector, the second argument for message send function. We should look upward to see what is the selector, and in this case, the selector comes from X register 20, and which stores a string constants request ID map. Finally, we know the deallocated object is property request ID map. Then we can explore our code base to check this variable. We have to check in our code base if any unexpected modification occurred from different threads, and any possibility that this object is used after freeze. If there was, how did it happen? So now you may ask, how about Swift? You may say that Swift has the mechanism to make sure memory isn't accessed after it is being deallocated, and multiple accesses to the same areas of memory don't conflict. But the truth is, the potential conflicts in memory access still can occur. I would like to show you another case about memory address in Swift. I wrote some demo code. Here I have a structure shelf, and it has a property books, which is arrayed. When I try to add more books to this array from different threads. Something unexpected happened. When I try to add a book from different threads, different queue, an exe bad access exception happens. The exception reason in the crash report shows there is something goes wrong when the app was trying to access a memory address which ends with 8CB0. From the backtrace of the crash report, I got the offset from the base address of Swift called dynamic library. Previously, I have disabled this dynamic library in Hooper. Let me show you how to disassemble a dynamic library from the system. Firstly, you have to download the system binary from website, or you can extract this binary from a jailbreaking device. So from this website, I already download some IPSW file. I choose the related iPhone version file for the corresponding crash report, and then I decompress it. So I use Hooper to open this already depressed file. I choose System, Library, Cache folder, and choose the dynamic library and opened it. And here I can search the Swift core library. Yeah, loading. So let's go back the crash report for this Swift demo. I didn't symbolicate this crash report, but I still can get the offset value here and use this offset to go to this line of assembly code where the crash happened. So now I just jump to that line of code. This is a load function in Swift release DEALLOCATED function. In the beginning of this Swift release DEALLOCATED function, the register x0 stores the value of the object which is going to be released, and then it loads this value into the x8 register, and then subtract 10 from this value. Finally, we got the address of the object which is going to be released. It ends with the 8CB0, but unfortunately, when the app tried to access this value ending with B0, the exe bad access exception occurs. Also from the exception type section, we know this address is far away from valid memory region, and we can say that this object address is invalid. In this Swift demo and in the backtrace of the crash report, we can also know the crash actually happened in the shelf structure in its add method, and we try to add a book to the books array, and something goes wrong inside this array append method. So what we have to do is to either to put this add operation into one serial queue, or we can add some lock. So wrap it up, I've shown you how to use Hooper to disassemble and how to use offset value to find out the address of the assembly code where the crash happened. And also I have shown you how to check the register state and the address in the exception type section, and how to find out the variable causing memory issue. This is the end of my sharing, and I hope this sharing can give you some inspiration when you encounter this kind of issue. So thank you for your time, and any questions?